Right. Good afternoon and welcome to this week's Iowa Learning Farms Conservation Webinar. I'm Matt Helmers with Iowa State University, ISU Extension and Outreach, and the Iowa Nutrient Research Center. And so we are very fortunate today to get to hear Dr. Bill Crumption talk a bit about wetlands and integrating drainage improvement and wetland restoration in Iowa. Dr. Crumption is a wetland ecologist at Iowa State University. He is a faculty member in the Department of Ecology, Evolution, and Organismal Biology. I just test myself to see if I can get that right. Dr. Crumption has also been heavily involved with both the undergraduate and graduate programs in environmental science at Iowa State throughout his career. I've had the good fortune of working with Dr. Crumption since I came to Iowa State in 2003. So with that, I will turn it over to Dr. Crumption. As always, if you have questions, feel free to type those into the chat box and we will get those to Dr. Crumption at the end of his talk. With that, Bill, the virtual floor is all yours.
Okay, and I'll move to what I think is a prettier slide, but the title. So I'm going to talk about integrating drainage improvements, meaning not new drainage, but replacing historical drainage, upsizing the mains to modern standards. This happens every year, multiple sites across the state as the drainage districts age out. And I'm going to look at the environmental and impacts of both improved drainage and the targeted wetlands that are restored at the base of those improved drainage systems. The upper Miss is characterized by extensive cultivated cropland, shown in brown, extensive drainage, shown in light brown, and elevated nitrate concentration. So this is just to orient people that aren't from here to our issues. The Iowa Nutrient Reduction Strategy recognized widespread degradation in water quality in Iowa, that we are a major contributor to Gulf hypoxia. Agriculture dominates nutrient loads, nitrogen and phosphorus both, and the strategy goal is a 45% reduction in nitrogen loads and phosphorus. And in the case of nitrogen, 41% of that reduction is to come from non-point sources. So the Integrated Wetland Landscape Systems Initiative, sometimes called the Iowa Plan, started some years ago. It was a pilot project to look at the opportunities to integrate improved drainage systems to mitigate farmed wetlands that might be in the catchments of drainage district systems that were being upgraded. The panel on the left, this is from Matt Luxembourg at the Department of Ag Land Stewardship. And the panel on the left shows the typical approach that was taken. That is, these are not protected under Clean Water Act, but they are swamp buster protected. So when a system is upgraded, if there are jurisdictional farmed wetland determinations, then they're mitigated to a bank, and the bank can sometimes be 100 miles away or more. That provides no water quality benefit from those restorations, but does the drainage improvement allows improved crop production. The plan was to instead mitigate by restoring wetlands at the base of that drainage network when it's upgraded. Still upgrade the system, but the mitigation of the FWs would be to that location. This provides an opportunity for some nitrogen reduction by that wetland. So we looked at 5 treatment sites. These were the Iowa pilot sites. Each one of these, so these sites were, each one of these integrated a wetland with an upgraded drainage district infrastructure. So the drainage coefficients might have been 1/8 of an inch, and they were upgraded, I think all of them to 1/2 inch or something similar. Those pilot sites, those drainage districts treat the wetlands that were integrated with those, treated about 12,700 acres of cropland and added nearly 100 acres of permanently protected wetlands. 4 of the wetlands that were added were actually CRIP sites. The 5th was a mitigation site for the farmed wetlands that were in some of these districts. We identified 5 reference sites. They're part of the Iowa CRIP monitoring program, and they're shown here in black. So these wetlands, they They're crepe wetlands, but they did not have, the catchments did not have upgraded drainage infrastructure. We refer to those throughout here as our references. So first, the impacts of improved drainage on cropland. I won't spend much time on this, but just this is from Matt Helmers. This is image on the left shows one of the systems, DD65, in 2008, prior to the drainage improvement, and 2015 after the drainage improvement. These were similar wet years, but 2008 was a bit wetter, right? So it's not a great test, but this shows wetness index. This is courtesy of Brian Gilder. The figure to pay attention to is one on the bottom. So DD15 North and 15 South. DD15 North was one of our pilots, and DD15, which had the improved drainage infrastructure, and DD15 South did not. And up until, if the first part of this figure from 1990 up through 2013 was prior to the drainage district improvement on DD15 North. And you can see that once that drainage district improvement went in place after 2013, DD15 North is clearly drier than 15 South. So it did have an impact. Environmental impact of improved drainage, looking at the hydrology and water quality. We've monitored these systems since they were implemented, putting close interval automated samplers at the inflows to those wetlands, and that represents the outflow from that drainage district. All of the surface and subsurface flow that exits that district is routed through this location. So we're not sampling just tile, we're sampling all of the flow. We also have flow measurement devices at these sites as well. This is an example of this is not for one of these sites, but just to give an example of what the data might look like. So the blue line here represents the discharge rates measured at that point. The red dots represent the nitrate concentrations. This is a pretty old slide. We have the automated samplers running now from about March through late November typically. Once the system freezes, those have to be pulled, and we continue to sample with grab samples every week. So what does this look like? So this simply gives you a sense of what the distribution of flow might look like, the water yield. So we normalize everything to area here. So this is the water yield exported from each pilot site catchment and each reference catchment over the 5-year period. These are the annual water yields, and the black dots are the reference sites. The red dots are the pilot sites. And the only purpose of this, it's a rank order plot. The lowest water yields during the driest years were around 0.2 meters per year, and the highest were above 0.6. Right? But the distribution that both pilots and reference sites are distributed along this entire range. That's also true for nitrogen. This is a nitrate yield in kilograms of nitrogen per hectare of catchment. Again, they're both distributed along the entire range. And the last is phosphorus. Again, the pilot and reference sites are all distributed across this entire range. These 4 sites that you see out at the far right side, those are reference sites with higher, noticeably higher phosphorus yield. It could be due to differences in practices. There could have been some manure plot. We'll explore that a little bit more deeply as we continue to get survey data from the landowners. Right? So these next few panels show these are notch box plots showing the water yield, nitrate yield, and phosphorus yield from the pilot sites in red and the reference sites in black. Right. So these are the pilot site water yields. These are the reference sites water yields. There's no significant difference among those systems. There's no evidence that the improved drainage increased water yields, and we would not have expected it to. May have modified the patterns of flow, but not the total water yield. Right? We would have expected it to decrease surface runoff, perhaps, but increase subsurface flow. Right? Nitrate export, the average nitrate yield for the pilot sites was about 47 kilograms per hectare, pretty high. Reference sites was about the same. Phosphorus, the phosphorus export from the pilot catchments was about 0.4 kilograms per hectare of catchment. And for the reference, it was about 0.6. That difference is not significant, right? Although you can see it's almost approaching significance, right? So the results to date suggest that the improved drainage, remember when I'm saying improved drainage here, I do not mean we take an undrained landscape and we improve it by installing drainage. These are already drained landscapes. They had existing drainage districts. They were drained. What happened is that the mains were replaced and upgraded to a higher drainage coefficient. So results suggest that improving the drainage to the higher modern coefficient did not increase the nitrogen and phosphorus export, and the nutrient concentrations and the mass loads from the improved drainage systems are no higher than those from the unmodified reference systems. Okay, so what about the project wetlands? Each of these pilot sites and reference sites had a wetland installed at the base. We maintained that these are identical to CREP wetlands installed anywhere, except 4 out of the 5 were in fact CREP wetlands. Only one of them was a mitigation wetland. So look at the effectiveness of the project wetlands in reducing the nitrogen loads. The way we monitor those is same as I described for the inflows, except now we have sites both at the inflow and outflow. So automated samplers at both the inflow and outflow. And we construct a complete water budget on these systems and a nutrient budget. By the way, the automated samplers collected samples every 6 hours, composited those into a single daily composite, preserved in the bottle when they're collected, and they're returned to the lab for analysis. So these are not the pilot sites or the reference sites. These are just examples of wetlands having really high nitrate removal efficiencies and low nitrate removal efficiencies. So if you notice these 3 panels, they're all, the lines are all the same. The red dots are nitrate concentrations entering a wetland. The green are the nitrate concentrations exiting the wetland, and the blue line is the inflow rates. You notice that the top one reduced the concentrations much more than the middle or the bottom, right? And that simply reflects the increased residence time. So that top wetland was either a large wetland for its catchment size, or it was a dry year, right? So there was a longer residence time, and the wetland had an opportunity to reduce the nitrate concentration by a much larger fraction. This is not mathematically, but conceptually, the inverse of hydraulic loading rate. Hydraulic loading rate is a very useful metric for modeling behavior of these systems. Hydraulic loading rate is the total amount of water loaded to the system divided by the system's area. So the more water loaded to the system, the lower the hydraulic loading rate, or sorry, the more water lowered to the system, the greater the hydraulic loading rate and the shorter the residence time. All right, the way that we analyze this data is we collected, as I said, the closed interval data. We had information on flows. We had information on the concentration of nitrogen in precip. We measured the inflows. We measured the outflows, had seepage losses. All of those are estimated directly from measured data. And the nitrogen reduction in the system is calculated by solving that mass balance. Same thing for phosphorus, right? It was done the same way. So the effect, the outcome is, any of you see me give a talk, you'll have seen this figure. This is looking at the effect of hydraulic loading rate and temperature on the nitrate removal efficiency, the percent nitrate removal. So as the hydraulic loading rate increases along the horizontal axis here, the percent removal goes down. Right. So as the hydraulic loading rate increases, the residence time decreases, and the percent removal goes down, right? Temperature does also have an effect. So the upward slope in this surface reflects the effect of temperature. Oops. So yeah, so this shows the effects of temperature, that upward slope on the surface, and this is what we call load weighted temperature. Flow weighted temperature would give you almost the same outcome. If you look down here at the far lower left side of the panel, this blue point at about 0.1 hydraulic loading rate, the temperature there was below 9 degrees Celsius, right? Now, was not the average temperature.
Okay, I'm watching a video. I'll come read it in a bit.
Joel, could you mute that, please? So the temperature wasn't the average temperature for the system or the year. It was a temperature weighted for when the load was coming. We don't really care what the temperature is in August if there's no flow, right? We care what the temperature is when the loads are delivered to the wetland. Right? And the warmest was over 18 degrees. Right? So a lot of range in temperature. Not that we can do anything about it for design, right? So what do you think about the effectiveness of the wetlands is, remember that temperature has an effect, and some of the variation you see at a particular hydraulic loading rate is due to temperature variation, but certainly not all of it. So this represents a nitrate removal efficiency versus average hydraulic loading rates for all of the CREP and pilot sites that we've monitored over 10 years, right? Pilot sites are the red dots here. The point of this graphic is to show you that the pilot sites behave just the same as any other wetland that we have constructed under the Iowa CREP. Right now, hydraulic efficiency, nitrate removal efficiency does not tell the whole story. The percent removal at a very hydraulic loading rate is very high, or sorry, very, very low, but the mass removal is not low. Right, so let's look at this. Here's a stylized plot of nitrate removal efficiency decay with increases in hydraulic loading rate. So as the system gets wetter, if it's really dry, you get almost 100% removal, right? And as it gets wetter and wetter and wetter, you get lower and lower. So a wetland that had occupied 1% of its catchment would be in this range of around 40% removal. Okay, in here, right? What about mass removal? Mass removal is different. So even though at the low hydraulic loading rates, you have nearly 100% removal, it's 100% removal of a very small load. So the mass removal is maybe only 500 kilograms per hectare. But out at higher hydraulic loading rates, say 0.3 here, that's mass removal is going to be 2,500 kilograms per hectare. Right. And that asymptote that you see here, that's real. It simply reflects the math of that system. Right. So this would be, the blue dots represent what the mass load would be if the flow rate average concentrations entering that wetland were 15 milligrams per liter. If you can cite the wetland somewhere where you have higher concentrations, 25, then you get the percent, the nitrate removal efficiency will be the same, but the mass removal will be very different. Right, so here, let's say 0.2, well, 0.3, right? We'd be removing 2,500 kilograms per hectare for 15 milligrams. If it was 25 milligrams, it would be almost 4,000. If we are able to get practices in the catchment that reduce the average nitrate concentrations, then that'll reduce the mass removal by the wetland that's downstream of it. That'll reduce the effect of any edge of field practice, right? The edge of field practices are designed to intercept the loads from those upslope systems. And if the upslope systems were able to eliminate the load, then the edge of field practices have nothing to work with. All right, so this is really preliminary information. I almost didn't include it because we haven't had a chance to really look at all the implications, right? But the wetlands do remove phosphorus. I've maintained that they cannot achieve their phosphorus reductions that are in the nutrient strategy. They're much less effective at phosphorus reduction than at nitrogen reduction, but they do reduce phosphorus. It's not as predictable. They'll always remove nitrate. They won't always remove phosphorus, but on average, these are for 70 some site years of data, not just the pilot sites, 70 some site years of data. And the bottom row in this table, the average total phosphorus load in across all of those years of data, and all those sites across the entire Des Moines lobe was over 100 kilograms per hectare. Now that's not export from the catchment. That's not phosphorus yield, right? This is what's loaded to the wetland. So a small wetland sitting below a really big catchment would receive a pretty high phosphorus load. And the load out averaged just well over 95 kilograms per hectare. So the load retained was just over 11, right? So around 10% retention of total phosphorus. If you look at the very top, total reactive phosphorus, the load in is 86. Most of the phosphorus exiting those drained catchments is in fact reactive phosphorus. Some of it's in the particulate fraction, but more than half of it is soluble reactive phosphorus, and the rest is immediately reactive phosphorus. The load out 68. So the wetlands on average removed about 20% of the reactive phosphorus. What it seems they're doing is they're transforming. So they're removing reactive phosphorus more efficiently than they are total phosphorus, and they're exporting this middle row. It's called non-reactive phosphorus. Just think about phosphorus having a fraction that's relatively labile and bioavailable. That's the reactive fraction. If it's sequestered into forms that are not bioavailable, that's the non-reactive fraction. And they're actually net exporter of non-reactive phosphorus. So they seem to be transforming, right? It's interesting to consider the way that we'll approach this is with a detailed simulations by each wetland on a daily time step to get at the details, because the wetlands differ so much from one another. But if we can think about the effects of inflow concentrations on phosphorus retention, it's been long known that the exchangeable fraction of phosphorus, so there is phosphorus that will adsorb and desorb to exchangeable sites, ion exchange sites in the bed of a system. Right? So if, in the way that would work, on the bottom left-hand panel here, I'm showing total phosphorus. So if the inflow concentration is really high, so there's an equilibrium point for a particular system. In the case of this, it's that red dotted line going across the panel here. So it's about 146 milligrams phosphorus per liter, right? This is, I'm sorry, micrograms phosphorus per liter, right? That crossing point, the green dashed line is the one-to-one line. If this was a completely conserved compound, the inflow concentration and the outflow concentration would be identical, except for any effects to the dilution or concentration from evaporation. And there's really none of that. We get the same amount of water going out as we do going in, except under drought years, right? Above this, so if the concentration is above 146 coming into the wetland, this red line out here, it shows that the wetland is reducing the phosphorus load. Right? It's a net sink. If the phosphorus concentration, on the other hand, is lower, the wetland is serving as a source. It's releasing phosphorus back up to that equilibrium concentration. Now, with total phosphorus, mechanistically, that's messy, because total phosphorus is a whole bunch of different kinds of phosphorus, right? If we instead look just at reactive phosphorus, the panel on the right, that crossing point is around 40 micrograms per liter for this particular wetland, right? It's around 40 micrograms per liter. We may have another wetland where the equilibrium point between its sediment and the water might be 150 for total reactive phosphorus. But for this wetland, it's quite low by Iowa standards, about 40. So that means that if the concentrations of phosphorus entering the wetland are above 40 micrograms per liter, the total reactive phosphorus is above 40 micrograms per liter, it's going to reduce the total reactive phosphorus concentration going out, which is a good thing. And overall, it's about a 20% reduction. Right? This one wetland kind of stood out because if you look at the range in these are the flow weighted average annual concentrations of phosphorus leaving the catchment and entering the wetland. And they range by almost an order of magnitude from below, well, probably an order of magnitude from below 40 to almost 400 micrograms per liter. We had no other wetland that we had multiple years of data on that had this range of variability. It was typically, you know, a fraction of that. We might have a twofold range in the from the lowest to highest annual flow weighted average, right? Right. As we dig through that data deeper, we think that because some of these systems were so stable that just a single application of manure at the wrong time by a single large operator in the catchment might show us a spike that year. All right, so we're going to dig deeper there. Okay, so overall, the effectiveness of the pilot wetlands, they perform as expected for an Iowa CWEP wetlands at the ratio. The pilot site wetlands had a ratio of about 0.73%. The pool was about 0.75% of the catchment area. They reduced nitrate loads, downstream nitrate and nitrate loads both by about 30%. Not 40 because they weren't at 1% ratios, right? And the nitrogen reduction by these 5 wetlands in the pilot was equivalent to retiring about 2,700 acres of cropland. So these 5 pilot project wetlands have a combined pool area of only 68 acres of pool, but they intercept over 9,000 acres of agricultural drainage. Right. So I'd entertain questions. While you're thinking about those questions, I'll show these 2. Right. So this is the Certified Crop Advisor Continuing Education Unit information. If you watch this, you can send this information to Liz Ripley. It's on this thing here. These are all recorded as well, so you can always go to the Iowa Learning Farms webinar page and pull up any a recent webinar recording, and the final slides will show you this information. Enough time for that, Matt?
And then maybe just a plug for the.
Yeah, that's the next slide.
Yep. And I'll type Liz's email in the chat box.
Well, wait a minute. Sorry. All right, I'm missing a slide.
Okay, I will. Well, while you're answering questions, I will look and put a plug in for the webinar for next week. We did have a couple questions that have come in already. And there was a question, can you give an idea of what might be a range of typical retention time in some of these wetlands?
Well, yeah, okay. It's anywhere from, so retention time is not a very useful metric. Hydraulic loading rate is how you would design these systems, right? So we don't pay a lot of attention to that, but it ranges. And do you mean the annual average retention time? Because the retention time ranges from during a flood from a few hours to during a drought, it's months and months and months and months and months, right? So it's just why
it was all summer at some of these, right? So okay, that's yeah.
So if you had an average hydraulic loading rate of 0.1 meters per day, And if your wetland was 1 meter deep, that would have a 10-day average retention time.
Okay. Great.
And if you increase the depth of the wetland from, say you had a half meter deep, actually the wetlands are close to half meter deep. So 0.1 meter hydroelectric rate, half meter deep, you have a 5-day retention time, right? If you double the depth to 1 meter, it increased the retention time to 10 days, and the hydraulic fish, the nitrate removal fish would not change at all. So you've increased it, so it's not responsive to detention time, it's responsive to the hydraulic loading rate.
Just to plug next week's ILF conservation webinar is Dr. Emily Zimmerman from Iowa State University. So tune in for that one. We're not done yet, but just a plug for Emily next week. Do you have another question here? Any work on multiple wetlands within a large drainage district? Also, how large, if from that ratio, seems to be acceptable with drainage districts?
I'm sorry, repeat that again, Matt.
Yeah. We can do one at a time. Any work on multiple wetlands within a large drainage district?
Multiple wetlands in series within a district, or so multiple wetlands. So yes, we have work on multiple wetlands in series. So we have a series here near Ames where there were 3 wetlands that were restored under CREP, one above the other. They're spread over about a 2-mile stretch. And the concentrations coming out of the first wetland or what goes in that particular site, by the time you got to the bottom of those 3 wetlands, the nitrate concentrations were a couple of milligrams per liter on average, annual average fluidity concentration. So those 3 in combination had a huge effect. Yeah.
Okay, next one there is also how large from the ratio standpoint seems to be acceptable with drainage districts?
The drainage districts have not expressed any opinion about this, as far as I know. We're still talking about a fairly small footprint. The individual landowners, so drainage districts, they typically do not own these. Right? They're an individual landowner. So it's how large is acceptable to the individual landowner. Some of them want them bigger because it's typically some of the most marginal ground they have. And some of them want to minimize the footprint. But the design pool is not based on those considerations typically. It's whatever we can achieve. We want to get 2%. But in a lot of locations, you just can't get 2% without having other impacts. But there's some that are well over 2%. So it's the pool area is there, and then the buffer is negotiated, and the buffer will range from for a 10-acre wetland, the buffer will range at the low end, maybe 20 acres, but they average about 30. They used to average a little higher, 30, 35 acres for a 10-acre pool, right? Ones that we're building now, what we call tile zone, the 10-acre wetland would only have about a 10 to 15-acre buffer around it. And the buffers are all planted in a native prairie mix of grasses and forbs. So a lot of co-benefit associated with that buffer.
Okay, the next one, with regard to retention time, wouldn't that increase temperature? I think you mentioned no way to control temperature or not meaningfully.
It would increase temperature a little in the summer if the tile flow coming in is cold, and it is if you've got good high flow rates, right? But the loads come almost always when the temperatures are low. So the loads are delivered. The flow rates we have when most of the load is delivered are elevated. And so the retention time is going to be short when the loads are, even though we design if you made it deeper, your Yeah, there would be, I was thinking about this, there would be conditions where if you make them deeper, you might see an increase in the average temperature. I have to think about that. But the during these high load, I mean, your light transparency, the penetration is pretty shallow. So there'll be a point at which making them deeper doesn't. Yeah, you're going to absorb all the light energy within the first 30 centimeters, right? It's still, I have to think about that. Yeah.
Okay, great.
That's an interesting question. Thank you.
Quick point, that DD 15 North that you mentioned, mitigation wetland, did that site also meet the CREP criteria?
Yeah, actually, it was designed as CREP, but enhanced. We actually made it larger than required by CREP. But the and there are a lot of other enhancements that don't affect the pool performance very much. But on this particular, this is DD 15 North, by the way, the image you see on the screen here. But you'll notice on the far left, sort of toward the top third of that panel, you can see an isolated wetland over in the buffer, right? And there's some of those scattered around in DD 15 North. Those isolated wetlands provide a different type of habitat than you see in the pool. You can have isolated wetlands in those buffers that are disconnected from the pool and are fishless, which make them better habitat for amphibians and yeah. Yeah, it's very close to CREP wetland. I think the CREP ratios are 2%, although they will build CREP wetland. We can build CREP wetlands with a larger ratio than 2%. And this one is over 2%.
So, all right, we got some great questions coming in. So one, your work is for Iowa. And I guess, have you looked at how like the same size wetland in, like a 1% wetland, its nitrate removal might vary as we look across the Corn Belt from wetter areas to maybe drier areas?
Yeah, there's we did a study with some USDA collaborators where we assessed the nitrate removal performance, imagining that we could put a wetland every square kilometer. So every, let's see, how many hectares would that be? Sorry. But about every 1,000 acres is what we were doing, right? So everyone is square kilometer. It was 400 hectares. So every 400 hectares, we would say, okay, let's disregarding whether we could actually do it or not. If you put a wetland in this location and you intercepted the flow from that 1,000 acres, how would it perform? And we did that from the upper Miss in Ohio all the way across to we didn't do the Missouri, but we did the whole Miss, right? The performance is similar. The opportunities are different, right? So we have you can't find places in Illinois or Indiana where you can put a wetland and intercept 2,000 acres of tile flow. You're intercepting ditch flow when you get to that scale in those eastern states, right?
There's another question here. Would trees as part of a wetland plan have any effect on nutrient reduction?
Not a measurable effect on nutrient reduction because the buffer itself. So if you got 30 acres of buffer, you're taking out of production, you've reduced the nutrient export from that catchment because you've retired ag land and made it perennial vegetation. And whether it was trees or vegetation or grasses and forbs, the big effect is that you're no longer cropping that ground. So you have that reduction. In terms of the reduction in the pool, the nutrient reduction is all in the pool, right? So unless the trees are in the pool, they're not going to do anything. And if they were in the pool, they still wouldn't be having an effect there.
Another question here. The slide showing that hypothetical asymptotic loading rate and percent removal. What
Yeah.
was the pool to catchment ratio there, and how does the plateau shift with the change in ratio?
So there's no ratio here. It is, let me get back to it. You're thinking fairly deeply about these patterns. So let's say is this the plot?
Yep, I think that's right. Yep.
So let's say 0.2 hydraulic loading rate. You can have 0.2 hydraulic loading rate by either making a wetland a different average size bigger. Let's say 0.1. 0.1 is, I think that's the average hydraulic loading rate in central Iowa for a wetland that was about 1% of its catchment. So if you made that wetland a 0.5%, instead of 1%, the hydraulic loading rate is going to go from 0.1 to 0.2. Right? If you went from 1% to 2%, it's going to go from 0.1 to about 0.05. Right? Right.
Oh, does that say? I mean, if, in the case that that you might get somewhat diminishing returns as we think about putting in a bigger wetland for a specific area.
Yeah, you do. Right. So.
Yep.
You get diminishing returns on average, right? But you don't get diminishing returns during those wet years when the highest loads are going. So we push for the biggest one you can build.
Yeah, and those years might be the ones we're most concerned about because they're the highest load years.
Yeah. In fact, we have a couple of manuscripts, Greg and David and I are working on that look at that both for the wetlands in terms of thinking about design, not designing for the average condition, but designing for the extreme condition. But then also about the upper Miss compared to the rest of the Mississippi Basin nitrogen loads. So.
All right.
Yeah.
I think those are the questions we have. I think this is really, really informative, Bill. As always, I really thank you for the presentation and thanks for folks for the questions and tuning in today. Again, as Bill mentioned before, this will be archived on the Iowa Learning Farms website. So if you miss something or you think somebody else might have interest in watching, please let them know and go and watch that. And then two last things, email ejukums@iastate.edu by 5 today with your CCA number if you're here for a soil and water credit. And also tune in next week. Dr. Emily Zimmerman will be giving the webinar. So same time, same place. And again, thank you, Bill, for an excellent presentation today.
And thank you, folks, for attending. And there were some interesting questions. I'll have to play with a few of those.